Hey, good morning, everybody. Happy Thursday. We're here today for our next installment on the Data Gold channel. Today, we're going to talk about data fallacies. And this was one of the daily data graphics that I posted last week. And I'll go ahead here and share my screen. Uh, but this is the data fallacies that great graphic provided to us by Gecko Board. And there's a bunch of fallacies here. Sometimes they're called biases. And this is really important as we continue to drive, AI and some of the other machine learning and models and stuff and algorithms. But in this particular view, there are 15 different things, and we're going to just take a look today at cherry picking. But I'll zoom in here a little bit and talk about each one. Cherry picking is where, and we'll talk about this more here in a minute, but where you're selecting the results that fit what it is that you want to say, and you may exclude the other ones. Data dredging is where you retest or you continue to use the same set of data until it says what you want it to say. Survivorship bias is when you draw conclusions based on an incomplete set of data. Cobra effect, you got to love that name, is where you select an incentive that accidentally produces the opposite result of what you want. The false causality is falsely assuming when two events appear related that one of them have caused the other. You've all probably seen those great correlation and causation discussions like ice cream and sales of ice cream cones and shark attacks. Gerrymandering is where manipulating the geographical boundaries, and that'll affect the data. Sampling bias is where you draw conclusions from a set of data that isn't representative of the population you're trying to understand. The gambler's fallacy is where you mistakenly believe that because something has happened more frequently than usual, that it's now less likely to happen in the future. So the Hawthorne effect is the act of monitoring someone can affect how they're doing it. So this is, where you're sampling data, and if people know you're sampling it, or you're watching them for a time study, they may do things differently. The regression fallacy is when something happens that's unusually good or bad, it will revert back towards the average over time. Simpson's paradox is when a trend appears in different subsets of data, but it disappears or reverses when the groups are combined. The McNamara fallacy is relying solely on metrics in complex situations and losing sight of the bigger picture. And this is an example of when something may actually happen and you're measuring it, but physically you're observing something and it actually is doing the opposite. And here they use this example of somebody, this tank coming down, but people will tend to believe the numbers, especially when that's all we preach. Hey, you should go read the numbers. There's overfitting, where you create a model that's overly tailored, you use a lot of features, you use all the columns in the data set. Publication biases shows that its findings are more likely to be published, that it distorts the impression of reality. And this is one of the things like with the fake news where you just flood the market with your message. And then the last one is when the dangerous summary metrics, which is the danger of, if you think of the old y equals f of x, if you really are paying attention to the y, sometimes it's the x's that can get you. So these are the 15 fallacies, and today we're going to take a detailed look at cherry picking. So this could be very meaningful in today's world, especially with the elections coming up. That you see you see the opposite candidates, and they're both basically claiming the same thing, and that's where it's interesting in politics, because it may not actually be a lie. It may actually be because they went ahead and they cherry picked the data. So they picked the data from the states or from the regions or whatever it is that supports, or they pick the study that supports what they want. And it's real data, but it's cherry picking. It's, hey, I can see that data. You could cherry pick, for example, when you first look at the data set, you may determine that, hey, I really like that data. It looks good, and I'm only going to pick this certain amount. So that's what we're going to talk about today. So the business problem here is we talked about data fallacies, and one of the things we're going to do is we talk about these fallacies is how you can counteract them, or what are some things that you can do to make sure that you don't fall prey to those biases. So today we're going to discuss the biases. We're going to define what cherry picking is, which I already did. We'll show some data cleaning after understanding the data set, and then we'll show some methods to deal with cherry picking. And these are the methods we're going to look at as random sampling, stratified sampling, and sensitivity analysis. As usual, this Python workbook will be available out on the YouTube channel, GitHub site. So today we're mainly going to use pandas, which is your typical data manipulation package in Python. We're going to use Seaborn, which is a graphical package for making nicer charts, and we're going to bring in Matplotlib library. So we'll go ahead and bring those in. And I'm using an extreme case here for cherry picking, but I just want to be able to show it well. So what we're going to do is there's a study on HIV, and what we're going to look at is what could happen if you cherry pick the data based on some very broad assumptions. So we'll go ahead and bring that in, and we'll take a look at the data. And you can see here what we have is the state name, that there's the sex of the person. There's HIV deaths per 100,000, HIV diagnosis per 100,000, and there's a variety of things in here that continue to go on. You'll notice there's also some missing data as well. So the initial data, and then this is very small, but the initial data file is only 168 rows, 25 columns. So what we're going to do here is we're going to look at the sex, and the cherry picking that I'm going to do is a bias that would say, women don't get HIV, which is obviously not true. They get it, but certainly we'll see what happens when you make that, or you might even say, women don't die from HIV. So when I look at this, what I notice in the data file, when I only see here in the header female and male, but the way this data file is set up is that there's female and male for a given state, and then they total it together and create a third entry for each state called all. So what we're going to do is, obviously that's not it's a calculation really. So we're going to go ahead and take that out. We're going to create a new data set called data 2. We're going to take that out, and you can see it went down to 112 rows. So now we only have male and female. And this is just a little chart to validate that. We only have male and female now. So what we're going to do here is we're going to say, okay, if I look at all the data, not by male or female, I can see here that my mean deaths across all the data, across all 112 rows, is 192. And if I do a box plot of that, this is my this is my male and female data combined. And you could see here my median is probably about 75. You saw the average was 192. And there's some outliers here. But when I run it by the sex, what I can see here is that we know that people know, just in general knowledge, that the HIV is more prevalent in males, and you could see here the median is much higher, and there's not the maximum here is 250, where here you're up around 700, 650, whatever. So if we said, okay, I'm just going to disregard the females, I'm going to say, I'm going to cherry pick. And again, this is an extreme example, but I'm going to cherry pick the males. So I'm going to create a new data set that basically drops the females. And when I do that, you'll see here, my median goes way up. And in addition, when I describe this, my mean also goes way up. So remember, for the combined data set, I was way down at 192. Now I'm almost 100 more than that, 291. So when I do that, it shows, again, it's only the males, but that obviously it skews the data. If I just look at the males, and again, this extreme case of cherry picking, but I just want to be able to illustrate it. So what we do here is we say, okay, one thing we could do is random sample. So when we do that, we can come in here and we can say, okay, I'm going to go ahead and look at the sample, and I'm going to basically sample half the data set, or 84 out of my 112 rows or whatever. So when I do that, and then when I do my box plot, you'll notice the random sampling is much closer to the, pulls of a random sample. It's much closer to the data using male and female. And when I look at it, you can see here again, it's still a little high again because it's random, but it's much more indicative taking a random sample than just saying, hey, let's just go after all the males. In stratified sampling, what we're doing here is we're saying, okay, I want to go ahead and I want to group it by sex and use that stratify. You use it as a stratification for the sampling. So when I do that, you'll see here that again now my median is a little bit, it's a little bit lower. And then when I look at it, again, I'm much closer now to that 192. So it's again, it's not, I haven't cherry picked the data. I've just used either random or stratified sampling. Another technique that I wanted to show here today is if you want to make a table, and this is one of the problems with working in Python is you may have to report the results. But here, what I did was I just said, okay, I'm going to use this tool called this program called Pretty Table. I'm going to call it. I'm going to show my column headers up here. I'm going to show my values down here, and this is so I don't have to keep scrolling up and down to show the comparison. Now these are a little bit different because every time I run this workbook, I'm going to get different sampling, but it's close enough to demonstrate here. So this creates this nice little table down here, which tells me, these are the data sets going over the top. So I have male and female, male, random, and stratified. And you can see here, here's an example of, my male and female, which is all my data, was 192. My male is much higher at 241. My random's closer, my stratified's closer to the male female. So the last piece I want to be able to show is my sensitivity analysis. And when I show that, what I have to do is I'm going to do a regression. I'm going to do a linear regression equation. And what I'm doing here is I'm going to go back to the all data set. I'm going to run the regression on the sex. I'm not going to cherry pick at this point. So when I do this, I'll create this function that will convert the male and female into numbers. And then when I do that, you can see here now you have ones and zeros. The other thing is as I'm getting ready to do a regression, I'll get an error if I don't convert these nons into numbers. So here I'm going to convert the data frame, the nons, into zeros. And now you can see when I do that, I have a bunch of zeros. So sensitivity analysis is used to understand how the output of the model or the decision that we're trying to make might change based on the conditions of the input factors. So when you in this particular case, it's almost like a design of experiments where you're gonna vary the factors, but you can see here it's really like a stress test for your decisions. So what I'm going to do here is I'm going to bring in for my regression. I'm going to look at only these variables: sex, HIV deaths per 100,000, HIV diagnosis per 100,000, HIV prevalence per 100,000, diagnosis percent share, HIV care, HIV diagnosis, HIV prevalence, and HIV PrEP. And those are going to be my X's. So out of the 25 columns, my Y is going to be HIV deaths. My X's are going to, I'm getting rid of all the other columns, or I'm not going to use them in the regression. So when I do that now, I'm going to use sklearn. I'm going to use linear regression. And then I'll run the model. I'll go ahead and fit it. And then what I'm going to do here is I'm going to print out the coefficients of for the different variables based on the regression. And the reason why I have to do that is because in the sensitivity analysis, I need to put that model in again. And when I do it, I'll explain this down here. So this is called sensitivity analyzer. And you'll notice here now I've taken again these variables from up here and I have to re-input them here and I have to define my model. So these are the variables I'm going to use. And again, they're the X's, not the Y. And then the Y part says return. And in this case, like if we wanted to say, for example, we wanted to add the values of sex and HIV deaths per 100,000, we would say return sex plus HIV 1,000, and that would add them together. In this case, I'm going to input the regression equation, which uses the coefficients. So that's why I printed out the coefficients. Now, you may notice that the coefficients are different. That's because every time it runs the regression, it's randomly it's a sample of the data. So this is one time I ran it. I'm not going to change it every time I do it. I just want to illustrate this. So now what I've done is I've taken these an earlier regression and I've put in here the equation and I put in here the coefficients. So again, now you can see I've put in and I've said, okay, here's my model, return, and then this is the calculation based on those coefficients. So I'll go ahead and I'll run that. And then the last part you have to do for your sensitivity analysis is to look at the you have to give it a dictionary. So for each one of the input variables, you have to put in a range. And so, for example, for each one of these, I looked at, okay, like for example, here, the HIV prep. You can see the minimum is 0, the maximum is about 47,000. So all I really did here was say, I'm going to put in a min, the midpoint, roughly the midpoint. Again, it doesn't have to be perfect because you're just trying to illustrate it. And then the maximum. And it really gives you a range, and we'll see how that plays out in the polygon charts or the hex charts. So now I'm going to go ahead and input this for each one, and then I'll go ahead and run it. And it takes I guess about 20 seconds to run. And it'll take about another 10 or 15 seconds to do the plots. So we could go into a big discussion about how to interpret these hex plots, but what you're really looking for is how sensitive are the different variables. And you can see here of all the variables in the model, it's going to show them one compared to the other. And as we page through, you have basically all those columns that I used in the model. And what you can see here is the red ones, and this is just the easy interpretation. The red ones are sensitive, meaning that the Y is sensitive to those input variables. And you can see here that sex is here. The red means that it's the redder the more sensitive. So here the sex is sensitive. Here it's sensitive, not so sensitive here, not so sensitive in this one, but here and here you can see. So a lot of red when it comes to the sex. So what that's telling you is that in the entire data set, that particular variable is very sensitive. Now, again, I made up this regression equation. I picked, or you could say I cherry picked those variables to actually run the analysis on, but I just made a very uneducated guess about what would drive HIV deaths. So what I did here to finish this off, to finish like the business of the analysis off, was I did go down. So before I go there, so here what this is really telling you is these variables that are showing red are sensitive, and you don't want to cherry pick based on those. So here, let's just go ahead and finish out the regression. So I went ahead here and I ran this just to see. These are the predicted deaths. And then here, when I did this, these are your regression metrics for, the performance metrics for a regression. So when I do that here, what it tells me, I'll help you interpret this. So what this really tells you is a couple things. You probably, the best, this is mean absolute error. This is mean squared error, which really doesn't mean much. It's harder to interpret. This is a root mean squared error, and then this is R squared. Normally, you're looking at MAE or RMSE, and the statisticians will tell you that the RMSE is the best metric. So what this is really telling you is that there's a 26 death death error um, against the again in this regression equation. So you have to ask yourself, if I go back, if I look at the initial sample here, 26 with a maximum of 250, it's about 10%, but with some outliers. But again, that's actually pretty good. Again, you'd have to make an educated decision based on what you want to do. And then the R square is telling you how much percent of variance is explained by the model. So again, that's 99%. Again, I made an educated guess. Higher the R square, the better. But again, you would know more when you actually do this. But again, this was a created equation using a real data set to show what could happen and how to avoid cherry picking. So I hope you enjoyed this video. Remember to subscribe to our channel, and we'll see you next week.